Tonight, we're going to walk into one of the strangest scientific discoveries of the past 5 years, and we're going to find out what it actually means for you, sitting here on this particular night, on this particular planet, looking up at a cosmos whose history we thought we understood. For about 30 years, the textbook story of how the universe grew up was clean. The Big Bang happened 13.8 billion years ago. The first hot plasma cooled into atoms 380,000 years later. The cosmos then went dark, in what astronomers called the cosmic dark ages, for somewhere between 100 million and 300 million years. The first stars eventually ignited, scattered faint made of pure hydrogen and helium. The first small galaxies began to assemble around them, gathering matter slowly. By about 1 billion years after the Big Bang, the first real galaxies, modest and chaotic and growing, were taking shape. By 2 billion years, you started to see something that looked like the cosmic web we see today. The full process was leisurely. It took time. That was the textbook. In 2022, the James Webb Space Telescope opened its eyes on that early cosmos and immediately began returning images that did not fit the textbook. Galaxies that were too big, galaxies that were too bright, galaxies that already had structure, galaxies that already contained heavy elements that were supposed to take generations of stars to forge, galaxies that looked, in the most disquieting cases, like adult galaxies, sitting only a few 100 million years after the Big Bang, when by every model in the standard playbook they should not have existed yet. The discovery has, in the language of the scientific community, broken something. Not the universe. The story we were telling about the universe. The cosmos has been quietly producing structure faster than our theories allowed, and the James Webb Space Telescope has been quietly showing us this is the case for nearly 3 years now. Almost every new release of high redshift data has tightened the pressure on the standard model of cosmology. Almost every new survey has added galaxies that, according to the textbook, should not be there. Tonight, we're going to walk slowly through what this actually means. Not the headline version, which has been compressed into clickbait. The careful version, in which we'll look at what the textbook said, what the telescope found, why the two do not match, and what the mismatch implies for the cosmos and for your particular place in it. Before we get started, sit with one important framing. The discovery does not mean the universe is wrong. The universe is what it is. The discovery means our description of the universe is incomplete, possibly in interesting ways, possibly in deeply consequential ways. The cosmos is gently telling us that we did not understand its early childhood as well as we thought. The telescope is the messenger. The implications are what we're about to walk through. Tonight, we're going to walk through 5 specific things that the James Webb early galaxy data reveals. Each one is a separate facet of the same surprise. Each one has its own technical content. Each one has its own implications for what cosmology is and for what your place in cosmic history actually is. The 5 things are these. The first thing is that the cosmic timeline you were taught was in significant ways wrong. The standard timeline placed galaxy assembly on a comfortable schedule, with the first real galaxies forming over hundreds of millions of years. The James Webb data shows that galaxies the size of an average modern galaxy, with substantial stellar mass and observable structure, already existed within the first 300 million years of cosmic history. The textbook timeline has been compressed. The second thing is that star formation in the early universe must have been far more efficient than the models allowed. The standard models predicted modest star formation rates in the cosmic dawn era, limited by the slow cooling of primordial gas in low metallicity environments. The James Webb data shows much higher star formation rates than the standard predictions, by factors of 3 to 10 in some cases. The early universe was, by every available metric, busier than it should have been. The third thing is that supermassive black holes appeared at the centers of early galaxies much earlier than any conventional model of black hole formation could explain. The standard story was that supermassive black holes grew slowly through the accretion of matter onto smaller seed black holes, with the process taking hundreds of millions of years to produce the supermassive monsters we observe in mature galaxies. The James Webb data shows supermassive black holes, sometimes with masses of millions of solar masses, sitting at the centers of galaxies that are only a few 100 million years old. The black holes appear by every measure to be too big too soon. The fourth thing is that the standard model of cosmology, the lambda CDM framework that has dominated theoretical work for 30 years, is now under serious strain. The model worked extraordinarily well for the cosmic microwave background measurements, for the large-scale distribution of galaxies, for the Hubble expansion, for the abundance of light elements, for almost every test physicists could throw at it. But the early galaxy data, combined with several other tensions that have accumulated in recent years, is pushing the model to its limits. Whether the model survives in its current form, or whether it needs significant revision, is now an active question. The fifth thing is what all of this means for your particular cosmic moment. You're alive at a strange time. You're alive during a real-time revision of the textbook story of how the universe grew up. You're alive while the very early cosmos is being remapped, almost month by month, with each new James Webb data release. Your specific cosmic moment, sitting here tonight, is the moment in which the cosmic dawn era is becoming, for the first time in human history, directly observable. That moment is rarer and more interesting than most of the popular discussion acknowledges. 5 things, 5 facets of the same surprise. By the end of tonight, you will have walked slowly through each one with enough technical detail to feel the weight of what is happening, and enough perspective to see why this particular moment matters more than the usual cosmic story suggests. Pattern interrupt. The point of tonight is not to alarm you. The cosmos is fine. The data is informative. Cosmology is, in some ways, going through one of its most interesting periods since the discovery of the cosmic microwave background. What feels like a crisis from one angle looks, from another angle, like the kind of empirical pressure that produces real scientific progress. Tonight, we will sit with both feelings, the strangeness and the excitement, because both are appropriate responses to what is actually happening. Now let's begin with the first thing. The cosmic timeline you were taught was wrong. To understand what changed, we have to understand what the textbook timeline actually said. The standard cosmological model, refined over the past 30 years with extraordinary precision, made specific predictions about when and how the first structures in the universe should have formed. The predictions were not vague. They were detailed, mathematically explicit, and tied to specific physical processes. The story began with recombination, 380,000 years after the Big Bang, when the hot plasma of the early universe cooled enough for electrons to combine with protons into neutral hydrogen atoms. The cosmos became transparent at this moment, releasing the photons that we now observe as the cosmic microwave background. For the next several 100 million years, the cosmos was filled with neutral hydrogen gas, no stars, no galaxies, no luminous sources of any kind. This was the cosmic Dark Ages. During the Dark Ages, the slow gravitational dance of dark matter and gas began the long work of producing structure. Small density fluctuations, the same fluctuations we see imprinted in the cosmic microwave background, began to grow under their own gravity. Dark matter collapsed into halos. Gas flowed into the deepest gravitational wells. The standard models calculated in considerable detail how long this process should take and what the first luminous structures should look like. The first stars in the standard story should have formed somewhere between 100 and 200 million years after the Big Bang. They should have been massive, isolated and short-lived, made entirely of hydrogen and helium because no heavier elements existed yet. They should have died quickly in supernovae, scattering the first heavy elements into the surrounding gas. The first small galaxies should have begun to assemble around them shortly thereafter, with the assembly process taking hundreds of millions of years to produce anything resembling a recognizable galaxy. By the end of tonight, you're going to understand that this timeline, which has been taught in cosmology courses for decades, has been substantially revised by the James Webb data. The revision is not subtle. It is large enough that the entire chronology of the cosmic dawn has had to be reconsidered. The trouble began almost as soon as James Webb came online. The telescope was launched on Christmas Day of 2021 and reached its operational position at the second Lagrange point in late January of 2022. After a commissioning period of about 6 months, the first science observations began. The first deep field images were released in July of that year. Within those first images, astronomers were already identifying candidate galaxies at redshifts of 10 or higher, corresponding to cosmic times less than 500 million years after the Big Bang. The initial candidates were treated cautiously. High redshift galaxy candidates are notoriously difficult to confirm without spectroscopic follow-up, and the early James Webb candidates were no exception. The community waited for spectroscopy. The spectroscopy came in 2023. The candidate galaxies were, in many cases, real. The JD survey, the SEERS program, and several other dedicated James Webb projects began confirming galaxies at progressively higher redshifts. By the end of 2023, multiple galaxies had been spectroscopically confirmed at redshifts above 13. The current record holder, as of this moment, is JD's-GS-Z 14-0, confirmed in 2024 at a redshift of about 14.3. The galaxy is observed as it was approximately 290 million years after the Big Bang. By the standard timeline, this should have been before galaxies could meaningfully exist. The galaxy is, in fact, there, and it contains a stellar mass of roughly 400 million solar masses, which is to say a small but recognizable galaxy that should not exist yet according to the textbook. No one expects, on first hearing about high redshift galaxy data, that the discrepancy with the textbook would be this dramatic. No one predicts that a telescope launched only a few years ago would so completely reshape the field. Absolutely no one anticipates the way the timeline has had to be compressed to accommodate the new observations. Pattern interrupt. Picture, for a moment, what this means. A galaxy whose light we now see, after 13.5 billion years of cosmic travel, was already a recognizable galaxy when the universe was less than 3% of its current age. The galaxy was there. It was forming stars. It was structured. It was old enough to be considered a galaxy in any sensible usage of the word. By every prior expectation, it should not have been. The textbook timeline gave galaxies time to grow. The James Webb timeline has had to shrink that growth window dramatically. Galaxies appear, in the new data, to assemble far faster than the standard models predicted. The cosmic dawn era is not the slow, gentle epoch of small proto-galaxies the textbook described. It is a more compressed and dramatic period of rapid structure formation. Tonight we're going to spend a careful pass on the specific surveys and instruments that have produced the early galaxy data, because the experimental program behind these results is one of the most ambitious and well-coordinated observational campaigns in modern cosmology. The flagship program for cosmic dawn observations is JD's, the JWST Advanced Deep Extragalactic Survey. JD's is a collaboration between the European Space Agency, the National Aeronautics and Space Administration, and the Space Telescope Science Institute, with leadership from Daniel Eisenstein at Harvard and Pierre Ferrouille at the European Space Agency. The survey was designed to combine deep imaging in multiple infrared bands with spectroscopic follow-up of the most promising high redshift candidates. The total observing time allocation for JD's is more than 700 hours of James Webb time, making it one of the largest observing programs of the telescope's first observing cycles. JD's operates in two complementary modes. The imaging mode uses the NIRCam instrument to take very deep images of selected sky regions in 7 different infrared filters, ranging from about half a micrometer to about 5 micrometers in wavelength. The choice of filters is optimized to detect the characteristic spectral signatures of galaxies at high redshift, particularly the Lyman break that marks the rest frame ultraviolet edge of a galaxy's spectrum. The Lyman break shifts to longer wavelengths as redshift increases, and its position in the observed spectrum provides a reliable redshift estimate for candidate galaxies. The spectroscopic mode uses the Enriched instrument to obtain detailed spectra of the most promising candidates identified in the imaging mode. The spectra provide definitive redshift confirmation by measuring specific emission lines from elements like hydrogen, oxygen, carbon, and nitrogen. Without the spectroscopic confirmation, even the most carefully selected photometric candidates can sometimes turn out to be lower redshift objects with spectra that happen to mimic the high redshift signature. The spectroscopy converts candidates into confirmed measurements. Pattern interrupt. The combination of deep imaging and spectroscopic follow-up has made JWST one of the most productive Cosmic Dawn programs ever conducted. By the end of 2024, JWST had confirmed dozens of galaxies at redshifts above 10, several at redshifts above 12, and the current record holder, JWST-GS-Z14-0, at a redshift of approximately 14.3. Each confirmation represents a galaxy that has been definitively dated to a specific cosmic epoch, with the dating supported by the precise location of multiple spectral features. By the end of tonight, you're going to understand that the spectroscopic confirmations are the gold standard for high redshift galaxy observations. The photometric candidates, while important, are subject to various contamination effects that can occasionally produce false high redshift identifications. The spectroscopic confirmations eliminate these effects. A galaxy with a confirmed spectroscopic redshift above 13 is, by every reasonable standard, a galaxy at that cosmic epoch. The JWST survey is not the only Cosmic Dawn program. Several other major programs have contributed to the data. The SEERS program, led by Stephen Finkelstein at the University of Texas at Austin, has produced complementary observations covering different regions of the sky. The Cosmos Webb program, led by Caitlin Casey at the University of California, Santa Cruz, has imaged a larger field at lower spatial resolution, providing statistical samples of high redshift galaxies. The Primer program has added near-infrared imaging in additional fields. The PEARLS program has used gravitational lensing to enhance the visibility of the faintest distant galaxies. Each program has contributed its own unique perspective to the broader picture of Cosmic Dawn. The combined dataset from all these programs, as of the present moment, includes thousands of candidate high redshift galaxies and dozens of spectroscopically confirmed sources. The pattern across all the programs is consistent. The early universe contains more bright galaxies than the standard predictions allowed. The pattern is robust across multiple surveys, multiple instruments, and multiple independent analysis teams. The pattern is not an artifact of any single program or any single analysis approach. It is a real feature of the data. No one expects, on first hearing about the James Webb early galaxy observations, that the experimental program would be quite this coordinated and quite this productive. No one predicts that a single space telescope could produce in just a few years a fundamental reshaping of one of the most studied epochs of cosmic history. Absolutely no one anticipates the way the combined observing programs have transformed Cosmic Dawn from a theoretical reconstruction into a directly photographed epoch. Tonight, we're going to walk through one specific case study in detail, JWST-GS-Z 14-0, the current record holder for the most distant confirmed galaxy. The galaxy was identified as a high redshift candidate in JWST's imaging data, and was then targeted for spectroscopic follow-up with NIRSpec. The spectroscopy, published by Stefano Carniani and his collaborators in 2024, confirmed a redshift of 14.3, corresponding to a cosmic time of approximately 290 million years after the Big Bang. The galaxy has a stellar mass of approximately 400 million solar masses, which makes it a small galaxy by modern standards, but a substantial galaxy for its cosmic age. The standard models before the James Webb data would have predicted galaxies at this redshift to have stellar masses of perhaps a few million solar masses at most. The observed value exceeds the predictions by factors of 50 to 100. The galaxy is, in this strict quantitative sense, much more massive than it should be. The galaxy also has interesting chemical properties. The spectroscopic analysis reveals the presence of nitrogen and other heavy elements in its interstellar medium. The presence of these elements requires substantial prior stellar processing. Stars must have formed, lived their lives, and died in supernovae that scattered the heavy elements into the surrounding gas, all within the first 290 million years of cosmic history. The chemical evolution timeline implied by the data is, again, faster than the standard predictions allowed. By the end of tonight, you're going to understand that JWST-Z14-0 is, in many ways, the iconic example of the cosmic dawn surprise. It is too massive. It is too chemically enriched. It is too old for its cosmic age, in the sense that the processes required to produce its observed properties should have taken more time than was available between the Big Bang and the moment of observation. The galaxy is, by every measure, an empirical challenge to the standard model. What this leaves us with is a clearer sense of the experimental basis for the cosmic dawn revolution. The data is robust. The surveys are coordinated. The spectroscopic confirmations are solid. The pattern is consistent across multiple independent programs. The James Webb early galaxy observations are not a tentative or controversial result. They are a well-established empirical reality that the theoretical community is now grappling with. By the end of tonight, you're going to understand that this compression of the cosmic timeline is the first major implication of the James Webb data. It is not the only implication, but it is the foundational one. Everything else flows from the fact that the cosmos produced recognizable galaxies much faster than the standard story predicted. The second thing the James Webb data reveals is that star formation in the early universe was much more efficient than the standard models allowed. The compression of the timeline is not just that galaxies appeared earlier than expected. It is also that the galaxies, when they appeared, were brighter, more massive, and more rapidly forming stars than any standard prediction permitted. Tonight, we're going to walk into this carefully, because the star formation efficiency problem is in some ways even more challenging for the standard cosmological model than the timeline problem. The basic issue is this. In the standard story, the first stars formed from primordial gas that was almost entirely hydrogen and helium, with traces of lithium and beryllium. Gas at this composition cools relatively slowly, because the cooling channels available to molecular hydrogen are limited. Slow cooling means slow collapse. Slow collapse means slow star formation. The combination, in the standard models, produces a cosmic dawn era with modest star formation rates and gradual build-up of stellar mass over hundreds of millions of years. The James Webb data shows much higher star formation rates. The early galaxies are producing stars at rates that, in some cases, exceed the standard predictions by factors of 3 to 10. The total stellar mass in the cosmos at any given early epoch is, in the James Webb data, larger than the standard models predict. The early universe was, by every measure, busier than the cooling-limited gas physics of the standard models allowed. By the end of tonight, you're going to understand that this is one of the most active areas of current theoretical work. The cosmology community is, at this moment, trying to figure out what mechanism could produce the observed high star formation rates in the early universe. Several candidate mechanisms have been proposed. Each one has its own implications for the broader theoretical picture. The first candidate mechanism is that the initial mass function of the first stars was different from the standard assumption. The initial mass function describes how stars are distributed across different masses when they form. The standard assumption, based on observations of nearby star-forming regions, is that most stars form with relatively small masses, with a long tail extending to higher masses. If the early universe instead produced more high-mass stars relative to low-mass stars, the same total stellar mass would produce more light, because high-mass stars are much more luminous per unit mass. The galaxies would appear brighter than the standard predictions, even with the same underlying physics. Pattern interrupt. There are physical reasons to expect that the initial mass function in the early universe might be different from the modern one. The absence of heavy elements would have changed the cooling properties of the gas, which in turn would have affected the typical mass of the collapsing clumps that produced the first stars. The standard expectation, going back to work by Volker Brom, Tom Abel and others in the early 2000s, is that the first stars were typically more massive than modern stars, with characteristic masses in the range of 30 to 100 solar masses, possibly higher. If this expectation is correct, then the early universe should indeed produce more light per unit stellar mass than the modern universe. But the explanation has limits. Even with a very top-heavy initial mass function, the total star formation rates required to explain the James Webb observations exceed the standard predictions. The initial mass function adjustment alone is not enough. Other mechanisms must also be contributing. The second candidate mechanism is that the star formation efficiency, the fraction of available gas that gets converted into stars in a given time, was higher in the early universe. The standard models, calibrated against modern observations, assume star formation efficiencies of around 1 to 10%. The James Webb data may require efficiencies as high as 20 to 50% in some early systems. This would mean that the early gas was, in some sense, much more enthusiastic about forming stars than modern gas, with a much larger fraction of the available material ending up in stellar form. Why this might be the case is not yet fully understood. Several proposals have been advanced. One possibility is that the absence of heavy elements meant that supernova feedback, which normally regulates star formation by heating and dispersing the surrounding gas, was less effective in the early universe. Another possibility is that the high density of gas in the early universe, combined with the low background radiation, allowed gas clouds to cool and collapse more efficiently than they do in the modern universe. A third possibility is that some combination of these effects, plus other factors not yet identified, conspires to produce the higher efficiencies the data seems to require. The third candidate mechanism involves the role of dark matter halos. In the standard picture, the first galaxies formed inside dark matter halos that had been growing through gravitational collapse for tens to hundreds of millions of years. The mass and structure of these halos determined how much gas could accumulate at the center, and therefore how much stellar mass could form. If the early dark matter halos were either more massive or more concentrated than the standard models predict, the gas accumulation would have been faster, and the resulting galaxies would be more luminous. This explanation connects to broader questions about the nature of dark matter itself. Some proposed modifications to the standard dark matter picture, including warm dark matter and self-interacting dark matter models, predict different halo properties in the early universe than the standard cold dark matter model. If the James Webb data turns out to require these modifications, it would be a significant shift in the broader theoretical picture. No one expects, on first thinking about the early universe, that the answer to why the first galaxies are too bright could connect to fundamental questions about the nature of dark matter. No one predicts that observations of distant galaxies could constrain the properties of dark matter halos in the early universe. Absolutely no one anticipates the way the James Webb data has become a probe of fundamental cosmology rather than just an inventory of early galaxies. Walk with me through one specific case study, because the abstract numbers become more vivid with a concrete example. Consider the galaxy GN-Z11, originally discovered by the Hubble Space Telescope at a redshift of about 10.6, corresponding to a cosmic time of approximately 420 million years after the Big Bang. The galaxy was, at the time of its discovery in 2016, the most distant confirmed galaxy. The Hubble observations showed that GN-Z11 was bright, more luminous than the standard models predicted for galaxies of its age. James Webb has now observed GN-Z11 in much greater detail. The new observations confirm and deepen the original puzzle. The galaxy is bright. It contains nitrogen, carbon, and other heavy elements that should have required substantial prior generations of stars to forge. It hosts a supermassive black hole with a mass estimated at 1 to 2 million solar masses at its centre. By every measure, GN-Z11 is too developed, too chemically enriched, and too well structured for its cosmic age. By the end of tonight, you're going to understand that GN-Z11 is not an isolated anomaly. It is one of many examples of the same pattern. The James Webb data is filled with galaxies that are too bright, too massive, and too chemically enriched for the textbook timeline. The pattern is consistent across multiple surveys, multiple instruments, and multiple independent analysis teams. The pattern is real, and it is one of the central puzzles of current cosmology. Before we walk into the third thing, take a slow breath here. The story is about to take a brief turn into a different kind of conversation. We should pause now to acknowledge why this kind of slow, careful walk through the strangeness of modern cosmology exists at all. Tonight we're going to walk carefully through the pre-James Webb and post-James Webb timelines of cosmic dawn, because the contrast between the two is one of the most informative ways to feel the weight of what has changed. Before we get started, sit with the basic structure of the pre-James Webb picture. The picture had been developed over several decades, with major contributions from cosmologists working on simulations of structure formation, observations of high redshift quasars, and the early observations of the most distant galaxies accessible to the Hubble Space Telescope. By the time James Webb launched, the picture was detailed and quantitatively specific. The pre-James Webb timeline went something like this: recombination at 380,000 years after the Big Bang, cosmic dark ages from about 380,000 years to about 150 million years. First stars, called population the 3 stars, forming between 150 million and 200 million years. First proto-galaxies, small dim clumps containing the first generations of stars, forming between 200 million and 400 million years. First recognizable galaxies, with stellar masses of a few hundred million to a few billion solar masses, forming between 400 million and 700 million years. First substantial galaxies, with the kind of structure and mass that we associate with modern galaxies, forming between 700 million and 1 billion years. The standard expectation was that, before about 500 million years after the Big Bang, the universe contained only very small, very faint, very primitive systems. The first James Webb observations were expected to reveal the gradual build-up of structure during this era, with the observations becoming progressively more challenging as the redshift increased. The most optimistic predictions suggested that James Webb might just barely detect the brightest galaxies at redshifts around 15, but only at the limits of the telescope's sensitivity. Pattern interrupt. The post-James Webb timeline has had to be substantially revised. Galaxies with stellar masses comparable to the predicted galaxies of 500 to 700 million years are now observed at 300 million years. Galaxies with chemical compositions indicating substantial prior stellar processing are observed at the highest redshifts where any galaxies are observed at all. Galaxies with supermassive black holes at their centers are observed at 400 million years, when the standard formation mechanisms struggle to produce such black holes within the available time. The compression of the timeline is not subtle. It is large enough that the entire chronology of cosmic dawn has had to be reconsidered. Whatever processes were producing the first galaxies must have been operating faster than the standard models allowed, by factors of several in some cases. By the end of tonight, you're going to understand that this revision has implications for the broader cosmological picture that go beyond the immediate observations. if the early universe was forming structures significantly faster than the standard models predicted, then the conditions in the early universe must have been different in some way from the conditions assumed in the standard calculations. The differences might be in the properties of dark matter, in the cooling and star formation physics of primordial gas, in the strength and behavior of feedback processes, or in some combination of these. Several specific revisions to the pre-James Webb timeline have already been proposed. The first revision is the formation time of the first stars. The pre-James Webb estimate was around 150 million years. The post-James Webb estimate, based on the observed chemical enrichment of the most distant galaxies, may need to push this back to 100 million years or earlier. The first stars must have existed, lived their lives, and died, scattering heavy elements in time to enrich the gas that formed the galaxies we now observe at redshifts above 14. The second revision is the formation time of the first proto-galaxies. The pre-James Webb estimate was around 200 million years. The post-James Webb estimate, based on the observed stellar masses of galaxies at the highest redshifts, may need to push this back to 150 million years or earlier. The first proto-galaxies must have already been substantial by the time we observe their descendants at redshifts above 14. The third revision is the formation time of the first supermassive black holes. The pre-James Webb estimate was that supermassive black holes formed gradually through accretion onto stellar mass seeds over hundreds of millions of years. The post-James Webb estimate, based on the observed black hole masses in the most distant galaxies, may need to invoke direct collapse seed black holes or primordial black holes to explain the observed masses within the available time. No one expects, on first thinking about the cosmic dawn era, that the pre-James Webb timeline could be off by such substantial amounts. No one predicts that the first few years of James Webb observations would produce revisions of this magnitude. Absolutely no one anticipates the way the timeline has had to be compressed at essentially every stage of cosmic dawn. Now let's begin to walk through the implications for the broader scientific picture. The compression of the timeline does not mean that the standard model of cosmology is wrong in any fundamental sense. The model still works extraordinarily well for the cosmic microwave background, for the large-scale structure of galaxies, for the Hubble expansion, and for most other tests. The compression of the timeline is instead a sign that the standard model is missing something specific about the physics of the early universe, particularly the physics of how the first structures formed. The missing piece, whatever it turns out to be, has implications for several broader questions. The first implication is for the nature of dark matter. The standard cold dark matter model assumes that dark matter is composed of particles that interact only through gravity. Some proposed alternatives, including warm dark matter and self-interacting dark matter models, predict different behavior in the early universe, with implications for the formation of the first structures. The James Webb data, by constraining when and how the first galaxies formed, provides indirect constraints on the properties of dark matter. The second implication is for the physics of primordial gas. The standard models assume specific properties for the cooling and collapse of the first generations of gas. The James Webb data, by showing that the early universe was forming structure faster than the standard models predicted, suggests that these gas physics assumptions may need to be revisited. Specifically, the cooling efficiency, the fragmentation behavior, and the typical masses of the first collapsed objects may all be different from the standard assumptions. The third implication is for the role of feedback processes. In the modern universe, feedback from supernovae, active galactic nuclei, and other energetic processes regulate star formation by heating and dispersing gas. The standard models assume that these feedback processes were also operating in the early universe, with similar regulatory effects. The James Webb data may suggest that early feedback was less effective than assumed, allowing more efficient star formation. The reasons might involve the lower metallicity of the early gas, the higher gas densities, or other environmental factors. By the end of tonight, you're going to understand that the revisions to the cosmic dawn timeline are not isolated. They're connected to broader questions about the basic physics of the early universe. The James Webb data is, in this sense, providing constraints on several different aspects of fundamental cosmology simultaneously. The combined picture is one of substantial empirical pressure on the standard framework, with the response of the theoretical community still being worked out. What this leaves us with is a clearer sense of why the pre-James Webb to post-James Webb timeline revision matters. It is not just a recalibration of one specific epoch. It is a signal that something more fundamental may need to be revised. The fundamental revisions, when they come, will have implications across cosmology more broadly. The James Webb early galaxy data is, in this sense, one of the most important new empirical inputs to cosmology in the past 2 decades. Before we continue, why this channel exists. If you have made it this far into a careful examination of the James Webb early galaxy data, you're not the casual viewer the algorithm expects. You're the person for whom this channel was built. Long-form cosmology, told at the pace of sleep, with enough technical detail to actually feel the weight of the discoveries, rather than just the headline summaries, is not what the platform rewards. It is what we make anyway, because we believe the cosmos is more interesting when the questions are developed slowly rather than collapsed into viral fragments. If that resonates with you, the simplest thing you can do for the channel is to subscribe. Subscribing tells the platform that long, calm, careful work is worth surfacing for the next person who needs a quieter way to think about reality. If you have already subscribed, thank you. Truly. If this is your first long-form night with the channel, welcome. The queue contains many more nights like this one. A small additional note. If Spotify is where you find yourself on sleepless nights, consider following the show there as well. The audio versions are tuned for the same purpose, the same pace, the same care. We want to be a slow companion across both surfaces. Now, let us return to the data. The third thing waits. The third thing the James Webb data reveals is, in some ways, the strangest of all. Supermassive black holes were already present at the centers of galaxies that are only a few 100 million years old. The black holes are not small. They are not just beginning to form. They are massive, sometimes containing millions of solar masses, and they appear in the data far earlier than any conventional black hole formation mechanism can explain. Tonight, we're going to walk into this carefully because the early supermassive black hole puzzle is, in its own way, one of the deepest open questions in modern cosmology. To understand the puzzle, we have to start with what we know about how black holes normally form. The standard story has 2 main pathways. The first pathway begins with the death of a massive star. When a star with more than about 20 solar masses exhausts its nuclear fuel, the core collapses under its own gravity and produces a stellar mass black hole, typically with a mass of 10 to 100 solar masses. These stellar mass black holes are well understood. They are observed throughout the modern universe, and the physics of their formation is well established. The second pathway involves the growth of stellar mass black holes through accretion of matter from their surroundings. A black hole sitting at the center of a dense gas cloud can capture gas from the cloud and grow over time. The maximum rate at which a black hole can accrete matter is limited by the Eddington limit, which arises from the balance between the inward gravitational pull and the outward radiation pressure produced by the heated infalling matter. At the Eddington limit, a black hole's mass doubles in about 50 million years. By the end of tonight, you're going to understand why this matters for the early supermassive black hole puzzle. To grow from a stellar mass black hole, with about 100 solar masses, to a supermassive black hole with 1 million solar masses requires the mass to double about 14 times. At the Eddington limit, this would take about 700 million years of continuous accretion at the maximum possible rate. To grow to 1 billion solar masses, which is the scale of some of the supermassive black holes observed in the most distant quasars, would take more than 1 billion years at the Eddington limit. The problem is that James Webb is finding supermassive black holes at cosmic times less than 1 billion years after the Big Bang. There simply has not been enough time for them to grow from stellar mass seeds at the standard accretion rate. The math does not work. Pattern interrupt. Several proposals have been advanced to address this puzzle. None of them is yet fully accepted, but each one represents a serious attempt to explain how supermassive black holes could appear so early in cosmic history. The first proposal is super-Eddington accretion. The Eddington limit, while it is a standard upper limit on accretion rates, can be exceeded under certain conditions. If the geometry of the accreting gas allows radiation to escape through certain channels, while matter continues to fall in through others, the effective accretion rate can be much higher than the Eddington value. Some models suggest that super-Eddington accretion phases lasting only a few million years could substantially accelerate the growth of black holes in the early universe. If super-Eddington accretion was common in the cosmic dawn era, the standard timescale calculations would be modified accordingly. The second proposal is direct collapse black holes. Instead of starting with a stellar mass seed and growing through accretion, the proposal suggests that some early black holes formed directly from the collapse of massive gas clouds without ever passing through a stellar phase. The resulting black holes would be much more massive than stellar mass seeds, with initial masses of tens of thousands to hundreds of thousands of solar masses. These intermediate mass seeds would then need to grow by only a few factors of 2 to reach supermassive scale, which is much easier to accomplish within the available cosmic time. By the end of tonight, you're going to understand that the direct collapse mechanism requires special conditions. The gas cloud must be massive enough to produce a substantial seed, but it must avoid fragmenting into many small clumps that would form ordinary stars. The standard conditions in the early universe, with relatively low gas pressures and low metallicity, are favourable for the formation of a few direct collapse black holes, but only in specific environments. Whether enough direct collapse events occurred in the right places to seed the supermassive black hole population is an open question. The third proposal is primordial black holes. These are black holes that may have formed in the very early universe, within the first fraction of a second after the Big Bang, from extreme density fluctuations in the primordial plasma. Primordial black holes, if they exist, could span a wide range of masses, from microscopic to many solar masses. Some proposals suggest that primordial black holes in the intermediate mass range could have served as seeds for the supermassive black holes observed at high redshift. The primordial black hole hypothesis has the advantage of providing seed black holes that exist from essentially the beginning of cosmic time. The hypothesis has the disadvantage of requiring specific conditions in the very early universe that have not been directly confirmed. The status of primordial black holes is therefore unclear. They might be the answer to the supermassive black hole puzzle. They might not exist at all. The next decade of observations may help to discriminate. Now let's begin to walk through a specific case study, because the abstract numbers come into focus with a concrete example. Consider the black hole at the center of JWST, the galaxy we discussed earlier. The black hole mass, estimated from spectroscopic observations, is approximately 1 to 2 million solar masses. The galaxy is observed at a cosmic time of about 420 million years after the Big Bang. To grow to 1 million solar masses by this cosmic time, starting from a stellar mass seed at the Eddington limit, would require almost the entire available time, with essentially no breaks in the accretion. This is not impossible, but it is uncomfortable. Most stellar mass black holes do not accrete at the Eddington limit continuously, for hundreds of millions of years. They have periods of high accretion separated by periods of low or no accretion. The continuous Eddington accretion scenario is, in this sense, a stretch. The direct collapse scenario fits the JWST black hole much more comfortably. If the seed black hole had a mass of 10,000 to 100,000 solar masses, formed directly from gas cloud collapse a few hundred million years before observation, the subsequent growth to 1 to 2 million solar masses requires only a few factors of 2. This can be achieved with modest accretion rates over reasonable timescales. The direct collapse mechanism is, for this reason, increasingly favoured as the explanation for early supermassive black holes. but the direct collapse mechanism cannot be the whole story. Some of the most extreme cases, including supermassive black holes observed at redshifts close to 7, with masses already exceeding 1 billion solar masses, are difficult to explain even with direct collapse seeds and Eddington limit growth. These extreme cases may require some combination of direct collapse seeding and prolonged super Eddington accretion phases. The picture remains an active area of investigation. No one expects, on first thinking about cosmic structure formation, that the assembly of supermassive black holes would turn out to be one of the most active puzzles in modern cosmology. No one predicts that the James Webb Space Telescope would so substantially reshape our understanding of how the central black holes of galaxies came into being. Absolutely no one anticipates the way the early supermassive black hole puzzle has become a probe of fundamental physics, with implications for primordial black hole physics, accretion physics, and the relationship between black holes and their host galaxies. Tonight, we're going to walk into the specific seed mechanisms proposed for the early supermassive black holes, because the physics of each proposed mechanism is worth understanding in some detail, and the implications for broader cosmology are substantial. The first mechanism, direct collapse black holes, has been the subject of substantial theoretical work over the past 2 decades. The basic idea is that, under specific conditions in the early universe, a massive cloud of gas can collapse directly into a black hole without ever passing through a stellar phase. The resulting black hole would have a mass of tens of thousands to hundreds of thousands of solar masses, providing a seed that can grow much faster to supermassive scale than a stellar mass seed can. The conditions required for direct collapse are demanding. The gas cloud must be massive, with a total mass of at least several million solar masses. The cloud must be at low metallicity, because the cooling provided by heavy elements would cause the cloud to fragment into many small clumps that would form ordinary stars instead of a single black hole. The cloud must also be exposed to strong ultraviolet radiation, which prevents the formation of molecular hydrogen and thereby suppresses the cooling channels that would otherwise lead to fragmentation. The combination of high mass, low metallicity, and strong ultraviolet exposure is rare but not impossible in the early universe. By the end of tonight, you're going to understand that the direct collapse mechanism has been worked out in considerable detail by theoretical cosmologists, including Marta Volonteri, Mitchell Begelman, Zoltan Hyman, and others. The numerical simulations show that, under the right conditions, the collapse can proceed essentially monolithically, producing a single massive black hole rather than a cluster of small ones. The simulations are challenging because they require resolving a wide range of physical scales simultaneously, but the consensus is that direct collapse is, in principle, a viable mechanism for producing intermediate mass seed black holes. Pattern interrupt. The crucial question is how often the direct collapse conditions actually obtained in the early universe. If direct collapse was common, then the seed population would be large and the explanation of early supermassive black holes would be straightforward. If direct collapse was rare, then the seeds would be scarce, and additional mechanisms would be required to explain the observed populations. The estimates vary, but most recent work suggests that direct collapse was common enough to produce a substantial seed population, with the total number of direct collapse seeds in the observable universe possibly numbering in the millions to billions. The second mechanism, primordial black holes, has been the subject of revived interest in recent years. The basic idea, first proposed by Stephen Hawking and Bernard Carr in the 1970s, is that black holes could have formed in the very early universe from extreme density fluctuations in the primordial plasma. The fluctuations would have had to be much larger than the average fluctuations we observe in the cosmic microwave background, but specific mechanisms in the early universe could have produced them. The mass spectrum of primordial black holes, if they exist, depends on the specific mechanism of their formation. Different inflationary models, different reheating scenarios, and different phase transitions in the early universe produce different predictions for the masses and abundances of primordial black holes. Some scenarios produce primordial black holes with masses in the range of tens to thousands of solar masses, which would be ideal seeds for the supermassive black holes observed at high redshift. Other scenarios produce primordial black holes at much smaller or much larger masses. The primordial black hole hypothesis has the advantage of providing seeds that exist from essentially the beginning of cosmic time. There is no need to wait for the formation of stars or the assembly of gas clouds. The seeds are already in place when the cosmos becomes transparent to light at recombination. The subsequent growth to supermassive scale, by accretion onto these primordial seeds, can begin earlier and proceed more efficiently than growth from stellar mass seeds formed after the cosmic dark ages. No one expects, on first thinking about black hole formation, that the seeds for supermassive black holes might have existed from the very beginning of cosmic time. No one predicts that primordial black holes, originally proposed as a theoretical possibility in the 1970s, would become a leading candidate for the seed population almost half a century later. Absolutely no one anticipates the way the James Webb data has revived interest in primordial black holes after decades of relative quiet. The empirical status of primordial black holes is mixed. There is no direct detection of any primordial black hole. The various constraints on their abundance come from gravitational lensing of distant stars, from the absence of certain expected signatures in the cosmic microwave background, and from the dynamics of galaxies and globular clusters. The constraints rule out primordial black holes as the dominant component of dark matter in most mass ranges, but they allow a substantial subdominant population in the mass range relevant for supermassive black hole seeds. The third mechanism, super-Eddington accretion onto stellar mass seeds, has also received renewed attention. The standard Eddington limit on accretion rates assumes a particular geometry for the accretion flow and a particular relationship between radiation pressure and infalling matter. Under certain conditions, particularly when the accretion flow is highly non-spherical, or when the radiation can escape through specific channels, the effective accretion rate can exceed the Eddington limit by factors of 10 or more. If super-Eddington accretion was common in the early universe, then stellar mass black hole seeds could grow to supermassive scale much faster than the standard Eddington calculation predicts. The growth would be episodic, with phases of rapid super-Eddington accretion interspersed with phases of slower accretion or no accretion at all. The combined growth over the available cosmic time could plausibly produce the observed supermassive black holes from stellar mass seeds without requiring exotic seed mechanisms. What this leaves us with is that the three mechanisms are not mutually exclusive. The actual population of early supermassive black holes may have been produced by a combination of all three. Some may have formed from direct collapse seeds, some may have formed from primordial black hole seeds, some may have grown from stellar mass seeds through prolonged super-Eddington accretion phases. The relative importance of the three mechanisms is currently being investigated through both theoretical work and additional observations. Walk with me through what this implies for the broader picture. The early supermassive black hole puzzle is, in this sense, a probe of multiple aspects of fundamental physics simultaneously. It constrains the conditions for direct collapse, the abundance of primordial black holes, and the limits of accretion physics. Each of these constraints has implications for related questions in cosmology, gravitational wave astronomy, and particle physics. The puzzle is, in this sense, more than just an interesting anomaly. It is a window into several different open questions in modern physics. Hold this image. The supermassive black holes at the centers of the early galaxies are not isolated curiosities. They are connected to broader questions about the seed populations, the accretion physics, and the conditions of the early universe. The James Webb data, by constraining when and where these black holes appeared, provides empirical input to all of these questions simultaneously. The combined picture is one of substantial theoretical opportunity, with multiple mechanisms competing to explain the observations, and with the next decade of data likely to discriminate among them. Hold this image. The third thing the James Webb data reveals is that the centers of early galaxies were already occupied by supermassive black holes when the cosmos was an infant. The black holes are too massive to have grown from stellar mass seeds at standard accretion rates within the available cosmic time. They require either special seed mechanisms, special accretion mechanisms, or some combination of both. The puzzle is real, and it is reshaping how we think about galactic center black holes more broadly. What emerges from this is that the implications for galactic evolution are substantial. In the modern universe, almost every galaxy with a substantial central bulge has a supermassive black hole at its center. The mass of the black hole correlates with the mass of the bulge, suggesting that black holes and bulges grew together over cosmic time. The James Webb data, by showing that supermassive black holes were already in place when the first bulges were still forming, suggests that the relationship between black holes and bulges is more complex than the simple coevolution picture allowed. What this leaves us with is a third truth that connects directly to the second. The compression of the cosmic timeline is not just that galaxies appeared earlier than expected. It is also that the central black holes of those galaxies appeared earlier than expected, with masses that the standard formation mechanisms struggle to explain. The cosmos produced its central black holes faster than the textbook allowed, and the implications for the broader physics of galaxy formation are still being worked through. The fourth thing the James Webb data reveals is that the standard model of cosmology, which has dominated theoretical work for 30 years, is now under serious empirical strain. This is not the dramatic claim that cosmology is broken. It is the more measured claim that the model is being pushed to its limits, and the response of the theoretical community will determine whether the model survives in its current form or whether significant revisions are needed. Tonight we're going to walk into this carefully, because the question of whether the standard model needs revision is one of the most consequential open questions in modern physics, and the early galaxy data is one of the most important new pieces of evidence bearing on it. The standard model of cosmology, called lambda CDM, has two main ingredients beyond the ordinary matter we are familiar with. Lambda refers to the cosmological constant, the mysterious energy that drives the accelerating expansion of the universe. CDM refers to cold dark matter, the unseen matter that dominates the gravitational dynamics of galaxies and clusters. Together with the ordinary matter described by the standard model of particle physics, these three components make up the energy content of the universe in the lambda CDM picture. The model has been extraordinarily successful. It accounts for the temperature variations in the cosmic microwave background measured by the Planck satellite to within about 1% of the predictions. It accounts for the large-scale distribution of galaxies seen in the Sloan Digital Sky Survey and other galaxy redshift surveys. It accounts for the abundance of light elements produced in the first few minutes of cosmic history. It accounts for the gravitational lensing signals seen in deep cosmic surveys. It accounts for the Hubble expansion rate measured by supernova observations at large redshifts. The list of successes is impressive. What this means is that, despite these successes, the model has accumulated several tensions in recent years that are now beginning to add up. The James Webb early galaxy data is the most recent and one of the most prominent of these tensions, but it is not the only one. The combined weight of the various tensions has pushed the field into a period of active reassessment. Pattern interrupt. Let us walk through the main tensions, one at a time, because each one is informative and each one connects to the broader picture. The first tension is the Hubble tension. The Hubble constant, which measures the current expansion rate of the universe, can be determined in two main ways. Measurements based on the cosmic microwave background, combined with the lambda CDM model, give a value of about 67 km per second per megaparsec. Measurements based on nearby supernovae and the local distance ladder give a value of about 73 km per second per megaparsec. The two values differ by about 9%. The disagreement has been around for about a decade and has resisted easy explanation. The Hubble tension might be due to systematic errors in one of the measurements. It might be due to new physics, such as time-varying dark energy or exotic particles. It might be due to local underdensity effects that bias the local distance ladder measurement. The various explanations all have their proponents and critics. The tension has not been resolved, and it continues to be one of the most studied problems in modern cosmology. The second tension is the sigma-8 tension. Sigma-8 measures the amount of clumping in the matter distribution on scales of about 8 megaparsecs. Measurements from cosmic microwave background data give one value. Measurements from weak gravitational lensing surveys give a slightly lower value. The disagreement is at the few percent level, which is smaller than the Hubble tension, but still statistically significant. The sigma-8 tension may be related to the Hubble tension, or it may be an independent issue. The community is working on both. The third tension, and the one we are walking through tonight, is the early galaxy abundance. The standard lambda CDM model, combined with the standard models of galaxy formation, predicts a certain number density of galaxies at each redshift. The James Webb observations consistently find more bright galaxies at high redshift than the standard predictions allowed. The excess is not enormous, but it is consistent across multiple surveys and at multiple redshifts. The tension is real. Now, let's begin to think about what these combined tensions imply. The standard lambda CDM model is, in its core form, a remarkably simple description of cosmic history. It depends on a small number of parameters, all of which have been measured to high precision. The model works extraordinarily well across a wide range of observations. The tensions are not signs that the model is wrong in any gross sense. They are signs that the model may be missing something subtle but important. Several proposals have been advanced for what the missing piece might be. The most conservative proposals stay within the basic lambda CDM framework, but modify specific aspects of galaxy formation physics, including the initial mass function of the first stars, the efficiency of feedback from supernovae and active galactic nuclei, and the role of cosmic radiation in regulating star formation. These proposals can, in some cases, accommodate the early galaxy data without requiring fundamental changes to cosmology. Whether they can do so consistently with all the other observations is an active question. The more ambitious proposals involve modifications to the cosmological framework itself. These include time-varying dark energy, in which the cosmological constant evolves over cosmic time. They include modifications to general relativity at large scales, which would change the way matter clusters under gravity. They include exotic dark matter models, including warm dark matter and self-interacting dark matter, which would change the formation of dark matter halos in the early universe. Each of these proposals has its own theoretical motivations and observational predictions. Step back and you can see that the field is, at this moment, in a period of active reassessment. The standard model is not being abandoned. It is being tested more carefully than ever before, with the James Webb data providing one of the most important new constraints. The next decade will likely see substantial theoretical work aimed at determining whether the standard model can absorb the new data with conservative modifications, or whether more fundamental revisions are needed. Expectation. Cosmology is a settled discipline, with the standard model providing definitive answers to the major questions about cosmic history. Reality. Cosmology is, at this moment, in one of its most empirically active periods, with multiple tensions accumulating and the standard model being tested more thoroughly than at any time in the past 2 decades. No one expects, on first thinking about modern cosmology, that the field would be in such an active state of reassessment. No one predicts that a single space telescope launched only a few years ago would so substantially reshape the empirical landscape. Absolutely no one anticipates the way the combined tensions, taken together, are pushing the field toward what may turn out to be one of its most consequential periods of theoretical development. The most recent developments in the field have come from DESI, the Dark Energy Spectroscopic Instrument at Kitt Peak. DESI is a galaxy redshift survey that has been producing precision measurements of the cosmic expansion history. The DESI Year 1 results, released in 2024, provided suggestive evidence that dark energy may not be exactly a cosmological constant, but may instead be slightly evolving with time. The result is not yet definitive. It is, however, suggestive enough that the community is taking it seriously. If confirmed by subsequent data, the result would represent one of the most significant changes to the standard model in decades. Tonight, we're going to sit with the implication. The combined picture, taking all the recent tensions together, is one in which the standard model of cosmology may be in the early stages of revision. The revision is not certain. It could turn out that the various tensions are explained by improvements in our understanding of complex astrophysics, without requiring fundamental changes to the underlying physics. But it could also turn out that the standard model needs significant modification, with implications for our understanding of dark energy, dark matter, and the basic physics of cosmic evolution. Hold the thought. We are alive at a moment of substantial scientific change in cosmology. The James Webb early galaxy data is one piece of a larger pattern. The combined pattern is pushing the field toward what may turn out to be a new era of theoretical work, with potential implications for the deepest physics of the cosmos. Tonight, we're going to walk carefully through the specific cosmological tensions that, taken together with the early galaxy data, are putting pressure on the standard model. Each tension is a measurement that does not quite fit the standard predictions. Each one has its own technical content and its own community of researchers working on it. The combined picture is more substantial than any individual tension alone. The first tension, and the most studied, is the Hubble tension. The Hubble constant is the current expansion rate of the universe, conventionally expressed in units of kilometers per second per megaparsec. It is one of the most fundamental parameters in cosmology. Its value determines, among other things, the age of the universe, the size of the observable universe, and the rate at which structure has formed over cosmic time. The Hubble constant can be measured in two main ways. The first way uses the cosmic microwave background combined with the standard cosmological model. The Planck satellite, operating between 2009 and 2013, made the most precise measurement ever of the cosmic microwave background. The resulting Hubble constant, derived from the Planck data and the standard model, is approximately 67 kilometers per second per megaparsec, with an uncertainty of about 1%. This second way uses nearby astronomical objects whose distances can be measured directly. The standard approach builds a distance ladder, starting with parallax measurements to nearby stars, calibrating Cepheid variable stars against the parallax distances, and then calibrating type ER supernovae against the Cepheid distances. The type ER supernovae can be observed across cosmological distances, providing a measurement of the Hubble flow that does not depend on the cosmological model in the same way as the cosmic microwave background measurement. What follows from this is that the local distance ladder measurement, conducted by Adam Rees at Johns Hopkins and his SH0ES collaboration, gives a Hubble constant of approximately 73 kilometers per second per megaparsec, with an uncertainty of about 1%. The two measurements, both very precise, differ by about 9%. The disagreement has been around for about a decade and has resisted easy explanation. The Hubble tension has been investigated extensively. Various proposed explanations have been examined. Some have invoked systematic errors in one of the measurements. Some have invoked new physics, including time-varying dark energy, early dark energy, exotic particles, or modifications to general relativity. Some have invoked the possibility that we live in a local underdensity that biases the local measurement. None of these explanations has been definitively confirmed or ruled out. Pattern interrupt. The persistence of the Hubble tension is in itself significant. The cosmology community has been working on it for a decade, and the tension has not gone away. If anything, it has solidified as the measurements on both sides have been refined. The most recent measurements, including improved Cepheid calibrations and additional supernova samples, have confirmed the local value of approximately 73. The most recent cosmic microwave background measurements, including improved analysis of the Planck data and complementary data from other experiments have confirmed the value of approximately 67. The two measurements really do disagree. The second tension is the sigma-8 tension, sometimes also called the S8 tension. Sigma-8 measures the amount of clumping in the matter distribution on scales of about 8 megaparsecs in radius. The cosmic microwave background measurements predict a specific value of sigma-8 based on the standard model. Independent measurements made through weak gravitational lensing surveys like the Dark Energy Survey, the Kilo Degree Survey, and the Hyper-SU-Prime Cam Survey give slightly lower values. The discrepancy is at the level of about 3%, smaller than the Hubble tension but still statistically significant. The sigma-8 tension may be related to the Hubble tension. Some proposed explanations of the Hubble tension, including time-varying dark energy and modifications to gravity, can also explain the sigma-8 tension. Other explanations of the sigma-8 tension, including specific modifications to the dark matter properties, are independent of the Hubble tension. The two tensions might have a common cause, or they might be independent puzzles. The community is working on both. The third tension, and the one we've been walking through tonight, is the early galaxy abundance. The standard model, combined with the standard galaxy formation models, predicts a certain number density of bright galaxies at each high redshift. The James Webb observations consistently find more bright galaxies than predicted at multiple redshifts. The excess is not enormous, but it is consistent and statistically significant. The tension is real. Notice that several other smaller tensions also exist. The lithium problem, in which the predicted abundance of primordial lithium from Big Bang nuclear synthesis exceeds the observed abundance by a factor of 3, has been around for decades and remains unresolved. The age of the universe, when measured from old stellar populations, is consistent with the standard model only at the boundary of the allowed parameter range. The matter-power spectrum on small scales shows some hints of departures from the standard predictions that may or may not be significant. The combined weight of all these tensions taken together suggests that the standard model may need to be revised in some specific way. The most recent developments in the field have come from DESI, the Dark Energy Spectroscopic Instrument. DESI is a galaxy redshift survey operating from Kitt Peak in Arizona, designed to measure the cosmic expansion history with unprecedented precision. The instrument can simultaneously observe thousands of galaxies, building a three-dimensional map of cosmic structure across much of the observable universe. The DESI Year 1 results, released in 2024, provided suggestive evidence that dark energy may not be exactly a cosmological constant. The data suggest that the equation of state of dark energy, which describes how the pressure of dark energy relates to its density, may be slightly evolving with time. The standard assumption is that the equation of state is exactly -1, corresponding to a true cosmological constant. The DESI data hints at slight deviations from this value, with the deviations becoming more pronounced as one looks at later cosmic times. No one expects, on first encountering modern cosmology, that the cosmological constant might turn out to not be quite constant. No one predicts that the simplest version of dark energy, which has been the standard assumption for 30 years, might be in the process of being revised. Absolutely no one anticipates the way DESI, in combination with the other tensions we have walked through, may be signalling a substantial shift in the cosmological picture. The full implications of the DESI results, and of the combined tensions more broadly, will take years to work out. The next several data releases from DESI, plus complementary observations from the Vera Rubin Observatory, the Euclid Satellite, and the upcoming Nancy Grace Roman Space Telescope, will substantially sharpen our understanding of dark energy and of the broader cosmological picture. By the end of the 2030s, we should have a much clearer answer to the question of whether the standard model needs significant revision. What this leaves us with is a sense of why this particular moment in cosmology is unusual. Multiple tensions have accumulated. The standard model is under empirical pressure that it has not faced in decades. The next several years of data will likely resolve some of the tensions, sharpen others, and possibly produce surprises that no one is currently expecting. The cosmology community is, in this sense, in an unusually active phase. The textbooks of 2040 may differ in substantial ways from the textbooks of 2020, depending on how the current tensions resolve. The point worth taking away is that this is, in some ways, the most consequential implication of the early galaxy data. The data is not just rewriting the timeline of cosmic dawn. It is contributing to a broader empirical pressure on the standard model, one that may yet produce significant changes in how we describe the cosmos at its deepest level. The fifth thing the James Webb data reveals is something more personal. You're alive at a moment in human history when the cosmic dawn era is, for the first time, becoming directly observable. Your particular cosmic moment is rarer and more interesting than most popular discussions of the discovery acknowledge. Tonight, we're going to walk into this carefully, because the personal implications of being alive during a major empirical revolution in cosmology are worth sitting with slowly. The history of cosmology is short. The modern science of cosmology, in its quantitative form, is barely a century old. Before Edwin Hubble's 1929 measurement of the expansion of the universe, the question of cosmic history was not a scientific question in the modern sense. There were no measurements of cosmic age, no measurements of cosmic size, no measurements of when galaxies formed. The cosmos, as a subject of empirical investigation, came into existence with Hubble and his contemporaries. For most of the century since, cosmologists worked with telescopes that could see only a fraction of cosmic history. The Hubble Space Telescope, launched in 1990, could see galaxies as they were perhaps 1 billion years after the Big Bang. The most distant Hubble galaxies were observed at redshifts of about 10, corresponding to cosmic times of around 500 million years. The era before that, the cosmic dawn era when the first stars and galaxies were forming, was effectively invisible. Astronomers knew it must have happened, because the alternative was that the cosmos was empty in that era, but they could not see it directly. James Webb has changed that. The telescope's infrared sensitivity, optimized for exactly the redshift range of the cosmic dawn era, has made the previously invisible epoch directly observable. Over the past 3 years, the cosmic dawn has gone from being a theoretical reconstruction to being a directly photographed reality. The transition is, in the long history of cosmology, one of the most consequential single observational advances of the past century. What this picture tells us is that what it means to be alive during this transition. We are, in cosmological terms, the first generation of humans who can see the cosmic dawn directly. Every previous generation, going back to the dawn of astronomy, could only theorize about what was happening in the early universe. They could not observe it. We can. The capacity to see the cosmic dawn is, in this strict sense, new. Pattern interrupt. Sit with this for a moment. You're alive at a moment when humanity has, for the first time, gained the ability to see the conditions in which the first galaxies formed. Your particular cosmic moment, this specific window of years, is a unique privilege in the long history of conscious observation. The cosmos is being mapped at depths that no previous human could access. The instruments are improving, the data is accumulating, the implications are being worked out by people who, like you, are alive during this specific epoch. There is a deeper version of this point that connects to the specific timing of being alive during a paradigm-shifting period. The history of cosmology has had several such periods. The discovery of the cosmic microwave background in 1965 was one. The discovery of the accelerating expansion of the universe in 1998 was another. The current period, with the James Webb data and the accumulated tensions in the standard model, may turn out to be a third. Each of these periods has produced significant revisions to our understanding of the cosmos. The current period may be the most consequential since the 1998 dark energy discovery. What this means is that you're not just alive during a quiet era of incremental progress in cosmology. You're alive during a period of substantial empirical revolution. The textbook you grew up with may not be the textbook that future generations will read. The picture of cosmic history that is being assembled right now, in real time, may differ in significant ways from the picture that was standard even 10 years ago. The takeaway is that this has practical implications for how you should think about the cosmos. The standard picture is not finished. The empirical work is ongoing. New data is reshaping the field every year. The cosmos you're looking up at tonight is, in a real sense, not the cosmos that the textbook described. It is a cosmos in the process of being newly understood, with the understanding being assembled by the work of thousands of scientists across many countries. Now, let's begin to think about what this means for your sense of cosmic identity. The classical view of being alive in a particular cosmic moment treats that moment as essentially generic. The cosmos has been here for 13.5 billion years. You're alive for at most a few decades. Your moment is, by this view, just one moment among many. The cosmos you observe is the same cosmos that everyone observes. There is nothing particularly special about your specific cosmic time. The revised view, based on the current state of cosmological observation, is somewhat different. Your specific cosmic moment is the moment in which the cosmic dawn became directly observable for the first time. Your specific decade is the decade in which the standard model of cosmology entered its current period of empirical stress. Your specific years are the years in which the James Webb Space Telescope is producing the data that will shape cosmology for the next generation. The cosmic moment you're alive in is not generic. It is specific. It is one of the more interesting cosmic moments in the brief history of cosmology as a science. No one expects, on first thinking about being alive at a particular time, that the specific time would have such a measurable impact on what cosmic data is available to you. No one predicts that the question of when in human history to be alive would have a cosmologically significant answer. Absolutely no one anticipates the way this specific epoch of your existence shapes what cosmic information you have access to. Take a moment to sit with this. You're alive at the start of a major empirical revolution in cosmology. The revolution may turn out to be more consequential than the dark energy discovery of 1998. It may, depending on how the current tensions resolve, fundamentally reshape our understanding of how the universe grew up. You're watching the early stages of this revolution unfold. You're alive during a particularly active period of cosmological discovery. The data is being collected as you sleep tonight. The papers are being written as you wake up tomorrow. The implications are being worked out by people whose work in the decades to come will shape the textbooks of future generations. Hold this image. Your cosmic moment is not generic. Your cosmic moment is one of the more empirically active periods in the brief history of cosmology as a science. The cosmos, in its quiet and patient way, has given you access to data that no previous human generation could have seen. The cosmos is, in some sense, showing you what is happening in its early childhood, at a level of detail that was previously unavailable. What becomes clear is that this is perhaps the most personal implication of the James Webb data. The data is not just about the cosmos, it is about you, sitting here, alive at this particular cosmic moment, with access to images of the cosmic dawn that no previous human could have seen. The cosmic dawn is in your night sky now, in a way it was not in any previous era of human observation. Your particular cosmic moment is privileged in this specific sense. Slowly we sit with the broader implication. The cosmos has produced you, alive at this particular time, with access to this particular set of cosmic data. The data is showing you that the standard model of cosmology may be in the early stages of revision. The data is showing you that the cosmic timeline you were taught was wrong in significant ways. The data is showing you that galaxies grew up faster than the textbook allowed, that supermassive black holes appeared earlier than expected, that the cosmos was busier in its infancy than any standard model predicted. Tonight, we're going to walk through one more piece of the cosmic dawn picture that the James Webb data has been illuminating. the era of reionization, when the first luminous sources began to ionize the neutral hydrogen that filled the cosmos after recombination, is one of the most important transitions in cosmic history, and the new data is providing fresh insights into how and when it happened. The basic picture is this. After recombination at 380,000 years after the Big Bang, the cosmos was filled with neutral hydrogen gas, transparent to most wavelengths of light, but opaque to ultraviolet radiation. The opacity to ultraviolet light meant that, even after the first stars began to form, their ultraviolet output could not propagate very far through the intergalactic medium. The cosmos was, in this era, dark in the ultraviolet, with the radiation from individual sources being absorbed by the surrounding neutral gas within relatively short distances. The first stars and the first quasars eventually produced enough ultraviolet light to begin ionizing the hydrogen around them. The ionization happened in patches, with bubbles of ionized gas growing around individual luminous sources. The bubbles grew larger as the sources produced more ultraviolet light. The bubbles eventually merged, producing larger ionized regions. The process continued until the entire intergalactic medium was ionized, at which point the cosmos became transparent to ultraviolet radiation. This complete reionization is estimated to have happened around 600 to 800 million years after the Big Bang, based on observations of distant quasars and absorption signatures in their spectra. What surfaces from this is that reionization is one of the most important transitions in cosmic history, because it marks the moment when the cosmos went from being mostly dark to being mostly visible. Before reionization, even powerful luminous sources could illuminate only their immediate surroundings. After reionization, light could travel freely through the cosmos for billions of light years. The conditions for the modern observable universe were established at the end of reionization. The James Webb data has provided important constraints on the timing and physics of reionization. The early galaxy observations show that there were already substantial populations of luminous galaxies during the cosmic dawn era, more substantial than the standard models predicted. These galaxies, with their high star formation rates and active galactic nuclei, would have been efficient producers of ultraviolet radiation. The total ultraviolet output of the early galaxy population, integrated over the cosmic dawn era, may have been sufficient to drive reionization on the observed timescales. Pattern interrupt. There has, however, been a long-standing puzzle about reionization. The standard models before the James Webb data struggled to produce enough ultraviolet radiation to complete reionization by the observed end time. The early galaxy populations, as estimated from Hubble Space Telescope observations, were either too few or too inefficient at producing ultraviolet output to ionize the cosmos within the available time. The puzzle was sometimes called the photon budget problem. The James Webb data may help resolve the photon budget problem. The newly observed populations of bright early galaxies, with their high star formation rates and substantial ultraviolet output, may provide the missing photons that the previous estimates were lacking. The total ultraviolet contribution from the brightest early galaxies, plus contributions from active galactic nuclei powered by the early supermassive black holes, may add up to enough output to complete reionization on schedule. What this leaves us with is that this is one of the more positive implications of the cosmic dawn surprise. The earlier galaxy populations that the James Webb data has revealed may actually help explain a problem in the standard model rather than create a new one. The early bright galaxies and their associated active galactic nuclei may be the missing photon sources that the photon budget problem required. The first stars themselves, the so-called population 3 stars, deserve a more detailed treatment. Population 3 stars are the very first generation of stars to form in the cosmos. They contained no heavy elements at all, because no prior generations had existed to produce them. They formed from pure hydrogen and helium gas, with only trace amounts of lithium and beryllium left over from Big Bang nucleosynthesis. The properties of population 3 stars depend sensitively on the chemistry of the primordial gas. Without heavy elements, The gas cooled less efficiently than gas in modern star-forming regions. The less efficient cooling led to higher characteristic masses for the resulting stars. The standard theoretical estimates suggest that population 3 stars were typically much more massive than modern stars, with characteristic masses in the range of 30 to several hundred solar masses, possibly higher. Massive stars produce more luminosity per unit mass than smaller stars. A population star of 100 solar masses produces 10,000 times the luminosity of the Sun. The ultraviolet output of such a star is particularly intense, with the radiation spectrum peaking in the extreme ultraviolet, where it can efficiently ionize hydrogen. A modest population of population 3 stars, distributed across the cosmic dawn era, could have provided substantial ultraviolet output, contributing significantly to early reionization. No one expects, on first thinking about reionization, that the resolution of the photon budget problem might come from the discovery of brighter early galaxies than the standard models predicted. No one predicts that the James Webb data, while creating new puzzles about galaxy formation, might also solve old puzzles about reionization. Absolutely no one anticipates the way the cosmic dawn observations are reshaping multiple aspects of early universe cosmology simultaneously. Walk with me through what this implies for the broader picture. The James Webb data is not just providing new puzzles for the theoretical community to solve, it is also providing new information that may help solve old puzzles. The combined effect is a more dynamic empirical landscape than has existed in cosmology for some time. The early galaxy data is forcing revisions to the timeline. The reionization picture is being refined. The puzzles of supermassive black hole formation are being sharpened. The tensions in the standard model are being illuminated from a new direction. Hold this image. The cosmic dawn era, which for decades was a theoretical reconstruction based on indirect evidence, is now being directly observed for the first time. The observations are reshaping our understanding of how the first stars formed, how the first galaxies assembled, how the first supermassive black holes appeared, and how the cosmos transitioned from a dark plasma to a transparent universe filled with luminous structure. Each of these reshapings is, in its own way, substantial. The combined effect is one of the more interesting periods in the history of cosmology. What emerges from this is that this is part of what makes the current cosmic dawn observations so significant. They are not just adding new puzzles, they are adding new information across multiple aspects of early universe cosmology, with implications that extend well beyond the immediate observations. The James Webb data is, in this sense, one of the most informative new empirical inputs to cosmology in the past 2 decades. What this leaves us with is a picture of personal cosmic existence that is more interesting than the standard one. You're not just a passive observer of a cosmos whose history is settled. You're an active witness to a period of significant scientific change. The cosmos is, in some sense, communicating with you through the data being collected right now. The communication is mediated by the work of thousands of scientists, but the result is the same. You are alive at a moment when the cosmos is being newly understood, and your particular cosmic moment is privileged in this specific sense. Tonight, we're going to spend a careful pass on what the cosmic dawn data actually changes about how you might think of your relationship to the cosmos, because the personal implications are worth sitting with as carefully as the scientific ones. Before we get started, sit with the basic situation. You have been told throughout your life a particular story about how the universe grew up. The story was a careful product of decades of cosmological work. It was the best available account when it was being assembled. It was taught in textbooks, repeated in documentaries, and absorbed into the broader cultural understanding of cosmic history. The story said that the universe took its time. The first galaxies assembled slowly. The cosmic structures we see today were the result of billions of years of gradual gravitational work. The cosmos in this picture was patient. The new data shows that the cosmos was not as patient as the story suggested. The first galaxies appeared faster than the story predicted. The supermassive black holes grew faster than the standard mechanisms could easily explain. The cosmic dawn era was a more dramatic period of rapid structure formation than the textbook narrative described. The cosmos in the revised picture was busier in its infancy than anyone had expected. No one expects, on first thinking about cosmic history, that the basic narrative they were taught could be substantially revised within their own lifetime. No one predicts that the textbook chronology of the cosmos would turn out to need significant compression. Absolutely no one anticipates the way the early universe, examined directly with new instruments, turns out to be different from what the standard reconstruction predicted. Pattern interrupt. The first practical implication is for how you might think about the speed of cosmic change. The classical intuition, supported by the standard story, was that cosmic processes are slow. Galaxies take billions of years to form. Stars take millions of years to evolve. Cosmic structures emerge through gradual gravitational work. The intuition gave you a sense of the cosmos as a patient and unhurried place. The revised picture is somewhat different. The cosmos in its first few 100 million years was anything but patient. It was building structure rapidly, producing complex galaxies and supermassive black holes on timescales that the standard models struggle to accommodate. The cosmos has, in this sense, more than one speed. It can be patient when the conditions favour patience. It can be rapid when the conditions favour rapidity. The cosmic dawn era was apparently a rapid period. The contrast with the slower later epochs is informative. Expectation. Cosmic processes are uniformly slow, taking billions of years to produce significant change. Reality. Cosmic processes can be much faster in certain epochs and certain environments, with the early universe being a particularly dramatic example. The second practical implication is for how you might think about the relationship between observation and theory. The standard model of cosmology was, until recently, treated as essentially settled. The major questions had been answered. The remaining work was filling in details. The James Webb data has changed this perception. The standard model is, for the first time in nearly 30 years, being seriously tested by new observations that challenge its predictions. The relationship between observation and theory is, in this period, particularly active. What this means is that this is part of why the current moment is interesting. We're alive at a time when the empirical landscape is reshaping the theoretical landscape, with the response of the theoretical community still being worked out. The next several years will likely see substantial theoretical development as researchers grapple with the new observations. The textbook chapter on cosmic dawn, in 2035, may differ in important ways from the chapter that was written in 2015. Now let's begin to consider what this implies for your sense of being alive in a particular cosmic moment. The standard view of being alive at a particular time treats that moment as essentially generic. The cosmos is, in this view, an unchanging backdrop against which individual lifetimes play out. The discoveries of any particular era are interesting but not unique to that era. The cosmos was here before you arrived. The cosmos will be here after you leave. Your particular cosmic moment is just one moment among many. The revised view is somewhat different. Your particular cosmic moment, this specific decade, is the decade in which the cosmic dawn era is becoming directly observable for the first time. Your specific years are the years in which the standard model is being tested by new data that may produce significant revisions. Your specific lifetime, if you happen to be alive during the right window, overlaps with one of the more empirically active periods in the brief history of cosmology as a science. The cosmic moment is not generic. It is specific. No one predicts, on first thinking about cosmic moments, that some moments would be measurably more empirically interesting than others. No one expects that the question of when in human history to be alive could have a cosmologically significant answer. Absolutely no one anticipates the way the timing of your existence shapes what cosmic information you have access to. The third practical implication is for how you might think about the limits of your own knowledge. The standard story gave you a particular picture of cosmic history. that picture you may have assumed was reasonably reliable. The new data shows that the picture was, in important ways, incomplete. The cosmos was doing things in its early childhood that the picture did not anticipate. The implication is that the cosmos is, in general, capable of surprising us in ways that our best models do not predict. This is, in some sense, the deepest practical implication of the cosmic dawn revolution. The cosmos exceeds our descriptions of it. Our best theories, however carefully constructed, are approximations to a deeper reality that has its own logic. The James Webb data is one demonstration of this. Future data from future instruments will likely produce other demonstrations. The cosmos is, in this respect, larger and stranger than our descriptions tend to suggest. Hold the thought. The classical relationship between you and the cosmos was one of confident knowledge. The cosmos was a particular thing. You knew, at least in broad outline, what it was. The revised relationship is one of more humble curiosity. The cosmos is a particular thing, but its particular features are still being mapped, and the mapping is producing surprises that the previous descriptions did not anticipate. The cosmos is, in this picture, larger than what you knew about it. Step back and you can see that this is not a discouraging conclusion. It is in some ways more interesting than the confident knowledge version. The cosmos has more to reveal than we have already understood. Future generations will know things about cosmic history that we currently do not. The work of cosmology continues. The picture continues to be refined. The understanding continues to grow. What this leaves us with is a personal cosmic picture that is, in some sense, more open than the standard one. You're alive in a cosmos that is still being mapped. Your particular cosmic moment is one in which the mapping is particularly active. The cosmos that contains you is, in important ways, still being newly understood. The work is not finished. The understanding will keep evolving. You are part of a generation that is alive during one of the more interesting periods in this evolution. Carefully, we address the 5 most common misconceptions about the James Webb early galaxy data directly, because each one has been widely repeated in popular discussion, and each one deserves a careful correction. Now, let's begin with the first misconception. The misconception is that the James Webb data has broken cosmology. This claim has appeared in numerous popular articles and viral videos. It suggests that the standard model has been definitively refuted, and that physics is in crisis. The technical reality is more measured. The standard model has been pushed to its limits by the new data, but it has not been definitively refuted. The model still works for most observations. The tensions are real, but they are tensions, not refutations. No one expects, on first hearing the popular framing, that the gap between the headline claim and the technical situation could be quite this large. No one predicts that the most widely repeated version of the story would so substantially overstate the actual scientific situation. Absolutely no one anticipates the way the news cycle has compressed a complicated and ongoing scientific discussion into a single dramatic claim. Before we get started on the second misconception, take a moment to acknowledge why the first one has been so persistent. The framing of the standard model being broken is dramatic. It generates attention. It produces clicks. The technical framing of accumulated tensions putting empirical pressure on the model is less dramatic but more accurate. The technical framing has, predictably, made less headway in the public imagination than the dramatic framing has. Now, let's begin with the second misconception. The misconception is that the early galaxies prove the universe is older than 13.8 billion years. This claim has appeared in various forms, sometimes with specific suggestions that the universe might be 26 billion years old or even older. The technical reality is that the age of the universe is determined primarily by the cosmic microwave background measurements, not by the early galaxy data. The CMB-based age of 13.8 billion years is robust and is not in question. The early galaxies appearing too soon for their age does not change the age of the universe. It changes our understanding of how fast structure formed within that age. What follows from this is that the popular framing of an older universe is a misreading of the data. The early galaxies are observed at specific cosmic times after the Big Bang. The cosmic time is determined by the redshift of the galaxy and the Standard Model parameters. The Standard Model gives a consistent age of the universe. The galaxies are appearing earlier than expected within that age. The age itself is not in question. The timeline of structure formation within the age is. The third misconception is that the James Webb data proves the Big Bang did not happen. This claim has appeared in various pseudo-scientific contexts, often with elaborate alternative cosmologies attached. The technical reality is that the James Webb data is fully consistent with the Big Bang model. The early galaxies are observed at exactly the cosmic times where the Big Bang model predicts they should be observable. The cosmic microwave background, which is the primary direct evidence for the Big Bang, is unaffected by the new data. The Big Bang model is not in question. The standard galaxy formation models within the Big Bang framework are expectation. Alternative cosmologies are being seriously considered by mainstream cosmologists in response to the new data. Reality. Alternative cosmologies have not gained any significant traction among working cosmologists, because the new data, while challenging the standard galaxy formation models, is fully consistent with the Big Bang framework that underlies the standard cosmology. The fourth misconception is that the James Webb data shows the universe is fundamentally different from what we thought. The popular framing often suggests that the cosmos has been completely reimagined. The technical reality is that the universe is not different. The cosmos is what it is. Our description of it is being refined. The refinement is happening at the level of galaxy formation physics, not at the level of fundamental cosmology. The Big Bang still happened. The cosmic microwave background still exists. The Hubble expansion still proceeds as observed. What is changing is the specific story of how the first galaxies assembled within this larger cosmic framework. No one predicts, on first encountering the popular framing, that the technical situation could be so much more measured than the headlines suggest. No one expects that the most dramatic versions of the story would so substantially overstate the actual scientific developments. Absolutely no one anticipates the way the gap between popular and technical accounts of modern cosmology has grown over the past few years. Hold the thought. The fifth misconception is that the James Webb data will be ignored by mainstream cosmologists. This claim appears in various contexts, often with conspiratorial undertones about a scientific establishment refusing to revise its theories. The technical reality is the opposite. The mainstream cosmology community has been actively engaged with the James Webb data from the moment it began to appear. Hundreds of papers have been published analysing the implications. Conferences have been held specifically to address the new observations. The theoretical community is, in fact, working through the implications with substantial energy. The standard model is not being defended through scientific stubbornness. It is being tested through the careful work of many researchers. Notice that the popular framing of an ignored or suppressed scientific result is not consistent with the actual behaviour of the cosmology community. The data is being analysed, the implications are being worked out, the model is being tested. The community is, in this sense, doing what science is supposed to do, with the new data being treated as a serious empirical challenge that requires a serious theoretical response. Hold this image. 5 misconceptions, each one widely circulated, each one wrong. The corrections do not diminish the importance of the James Webb data. The data is genuinely significant. The data is genuinely changing cosmology. The data is genuinely pushing the standard model. But the data is not breaking cosmology, not changing the age of the universe, not refuting the Big Bang, not fundamentally reimagining physical reality, and not being ignored by the mainstream. The technical situation is more measured than the dramatic version suggests, and the technical situation is also, in its own way, more interesting. What this leaves us with is a clearer view of why getting these misconceptions right matters. The popular framings, while they generate attention, also produce a less accurate picture of what cosmology is actually doing. The technical framings, while they are less dramatic, are also more honest about the current state of the field. The technical situation is one of substantial scientific work, with active empirical pressure on the standard model and with the response of the theoretical community still being worked out. This is, in its own way, more dramatic than the headlines suggest, because it involves real ongoing scientific change rather than a single rhetorical claim. Settle in as we spend a careful pass on what comes next in this story, because the cosmic dawn revolution is far from over, and the directions of current research are worth knowing. Before we get started, sit with the basic situation. The James Webb Space Telescope has been operating for about 3 years. The data is still being collected. The implications are still being worked out. The first wave of theoretical responses is appearing in the literature. The second wave, based on more complete observational programs and more sophisticated theoretical analysis, is just beginning. The full impact of the cosmic dawn data on cosmology will take a decade or more to be fully realized. Now, let's begin with the first specific development to expect. James Webb will continue to observe the cosmic dawn era for at least another decade. The observatory's mission lifetime is currently expected to extend to at least the early 2030s, with some estimates suggesting it could operate well into the 2030s or beyond. The observatory was designed for a 5 to 10 year mission. Conservative engineering estimates suggest a working lifetime of about 10 years, but the actual lifetime will depend on the available cryogenic propellant and the reliability of the various instruments. During its remaining operational time, James Webb will continue to push the high redshift frontier deeper. New galaxies at progressively higher redshifts will be discovered and confirmed. The statistical samples at each redshift will grow, allowing more precise measurements of the luminosity functions, the mass functions, and the chemical properties of the early galaxy population. The systematic uncertainties in the current results will be reduced. The boundaries of the discovery space will be pushed back. Soft pause. The second specific development to expect involves complementary observations from ground-based facilities. The Vera Rubin Observatory, currently coming online in Chile, will conduct the legacy survey of space and time, providing wide-field imaging of much of the southern sky. The Rubin data will not reach the same depths as James Webb at high redshift, but it will cover much larger sky areas and will produce statistical samples of early galaxies that are not feasible with James Webb's narrow field of view. The combination of Rubin and James Webb will be particularly powerful, with Rubin providing the breadth and James Webb providing the depth. Other ground-based facilities will also contribute. The extremely large telescope currently under construction in Chile will have a 39-meter primary mirror that will provide extraordinary sensitivity for high redshift spectroscopy. The giant Magellan telescope and the 30-meter telescope, also under construction, will provide additional complementary capabilities. By the end of the 2020s, the Cosmic Dawn observational program will be supported by an extraordinary array of ground-based and space-based facilities. The point worth taking away is that the third specific development involves the Euclid satellite and the upcoming Nancy Grace Roman Space Telescope. Euclid, launched in 2023 by the European Space Agency, is currently conducting wide-area infrared observations across much of the sky. The Euclid data will provide a complementary statistical sample of high redshift galaxies, with a survey area much larger than any James Webb field, but with somewhat shallower depth at the highest redshifts. The combination of Euclid statistics and James Webb depth will be powerful. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will have a field of view about 100 times larger than the James Webb field of view, with similar sensitivity in the relevant infrared bands. Roman will conduct wide-area surveys that will dramatically increase the size of the cosmic dawn sample. The combined data from James Webb, Euclid and Roman will, by the early 2030s, provide a comprehensive picture of the cosmic dawn era at multiple scales. The fourth specific development involves dark energy measurements from DESI and complementary programs. The DESI program, which we discussed earlier, is producing increasingly precise measurements of the expansion history of the universe. The next several years of DESI data will substantially sharpen our understanding of whether dark energy is exactly a cosmological constant, or whether it evolves with time. The answer to this question has profound implications for the broader cosmological picture and for the various tensions in the Standard Model. No one expects, on first thinking about the cosmic dawn revolution, that the full impact of the new observations could take a full decade or more to be properly understood. No one predicts that the next 10 years of observation and theoretical work could fundamentally reshape multiple aspects of cosmology simultaneously. Absolutely no one anticipates the way the current observational program represents perhaps the most consequential decade in cosmology since the discovery of the cosmic microwave background 60 years ago. The fifth specific development involves the theoretical response. The cosmology community is actively working on revised models of galaxy formation that can accommodate the James Webb data. New simulations are being run with different initial conditions, different baryonic physics, and different feedback prescriptions. The simulations are computationally expensive but are increasingly producing predictions that can be compared directly with the new observations. Over the next several years, the theoretical landscape will likely undergo substantial revision in response to the new empirical input. Before we get started on what all of this implies, take a slow breath here. The next decade of cosmology will be substantially shaped by the cosmic dawn data and by the complementary observations from other facilities. The combined empirical pressure on the Standard Model, plus the active theoretical response, will likely produce a substantially different picture of cosmic history by the early 2030s than the picture we have today. The work is in progress. The discoveries are accumulating. The understanding is evolving. Hold this image. We are alive at a moment in cosmology that is, by any reasonable measure, one of the most empirically active periods in the brief history of the field. The next decade will see substantial change in our understanding of the early universe, of galaxy formation, of supermassive black hole assembly, of reionization, of dark energy, and possibly of fundamental cosmology more broadly. The work being done right now is the work that will shape the textbooks of the future. What this picture tells us is that this is part of what makes the current cosmic moment unusual. The James Webb data, taken on its own, would be significant. The James Webb data, combined with the other developments we have walked through, and with the substantial theoretical response that is just beginning, may turn out to be the most consequential cluster of cosmological developments in decades. The textbooks of 2035 will reflect this work. The understanding of cosmic history that we leave to future generations will be substantially refined by the work of the current decade. What this leaves us with is a clearer sense of why the current moment matters. We're not just witnessing one specific discovery, however important. We're witnessing the early stages of what may turn out to be one of the more consequential periods in the history of cosmology as a science. The work is ongoing. The implications are still being worked out. The full impact will take time to be properly understood. But the current cluster of developments is, by any reasonable measure, substantial. For the rest of the night, sit with the 5 things we have walked through. The cosmic dawn era, which for the entire previous history of human astronomy was hidden behind the limits of our instruments, is now visible. The galaxies of that era, which the Standard Model predicted should be small, faint, and slowly assembling, turn out to be larger, brighter, and more fully formed than the textbook allowed. The supermassive black holes at the centers of those galaxies, which the standard formation mechanisms cannot easily explain, are already in place. The standard cosmological model is, for the first time in nearly 30 years, in a period of substantial empirical stress, and you, sitting in this particular room on this particular night, are alive at the moment when all of this is being worked out. Picture, for a moment, what the cosmic dawn era actually looked like in the new data. The James Webb Deep Field images contain thousands of distant galaxies in tiny patches of sky. Some of those galaxies are the most distant objects ever resolved by any telescope. The light from them, red-shifted into the infrared by the cosmic expansion, took more than 13 billion years to reach us. The galaxies, in their own time, were busy with star formation. They contained supermassive black holes. They were already producing the heavy elements that billions of years later would eventually find their way into your body. The cosmic chain that connects you to the cosmic dawn era is direct. The carbon in your cells, the oxygen in your breath, the iron in your blood, all of it traces back in some sense to early generations of stars that formed in the era the James Webb data is now revealing. Slowly, the camera in your imagination drifts outward. It leaves the room. It rises above the building, above the city, above the planet. It travels outward through the solar system, the galaxy, the local group, the cosmic web of galaxies. It pushes further, past the most distant galaxies that ordinary telescopes can see, into the redshift range where James Webb is now mapping. The galaxies at this distance are seen as they were within the first few 100 million years of cosmic history. They are not the fully developed galaxies of the modern universe. They are smaller, more turbulent, more chaotic. They are also, as the new data shows, larger and brighter and more developed than the standard model predicted. They are recognizably galaxies, in a way the textbook said they should not yet be. The camera continues outward. It approaches the cosmic dawn era in time and in space simultaneously. The first stars are scattered through the field, some of them already dying in the first supernovae that scattered heavy elements into the surrounding gas. The first heavy element pollution has begun. The first generations of stars are creating the chemical infrastructure that all subsequent generations will inherit. The cosmos is, in this era, busy with creation. It is laying down the conditions for everything that will follow, including the eventual emergence of the planet you're sitting on and the biology that produced your consciousness. The camera turns around and begins the long drift back, past the cosmic dawn era, past the cosmic web, past the local group, past the galaxy, past the solar system, past the planet, through the atmosphere, through the city, through the building, into the room, to the foot of the bed. You're still here. The version of you in this room, on this night, has not been replaced by any cosmological revision. The cosmos that produced you, including the cosmic dawn era we've been walking through, is exactly as it was. What has changed is our description of it. The cosmos is unchanged. The description is being updated. What this means for the way you experience the cosmos tonight is subtle. The night sky outside your window contains the same stars as it did before James Webb launched. The same galaxies are out there, the same cosmic structures, the same physical laws. The view, in the most literal sense, is unchanged, but the meaning of the view is slightly different. The cosmos you are looking up at, in addition to being the cosmos that contains the stars and the galaxies and the cosmic web, is also the cosmos in which the standard model of cosmology is currently being tested. The cosmos in which the cosmic dawn era is being directly observed for the first time. The cosmos in which one of the more empirically active periods in the brief history of cosmological science is currently unfolding. The cosmos has, in this sense, given you a small gift. It has placed you alive at a moment when the empirical work of understanding it is in a particularly active phase. The gift is not flattery. The cosmos does not care that you are alive, but the timing of your existence has produced a coincidence in which your specific lifetime overlaps with one of the more interesting epochs of cosmic observation. The data being collected as you fall asleep tonight is the data that will shape the textbooks of future generations. You're alive at the right time to be aware that this is happening. There is no need to hold all of this in your mind. The 5 things will keep their shape whether you remember the details or not. The James Webb data will continue to accumulate whether or not you can articulate its implications. The standard model of cosmology will be revised or vindicated based on the work of thousands of scientists across many countries, regardless of whether you follow the details. What matters tonight is that you have walked along the edge of one of the more interesting empirical periods in modern science, and you have done so gently, at the pace of sleep, with no urgency. The cosmos has been here for 13.5 billion years. The cosmic dawn era happened 13 billion years ago. The James Webb Space Telescope was launched 3 years ago. The data is being collected now. The implications are being worked out now. You're alive now. The convergence is not generic. It is, in its way, specific to this exact moment in cosmic and human history. Sleep can come whenever it wants now. The story has done its work. The cosmos that contains your sleeping body is the same cosmos that contains the cosmic dawn data. The same cosmos that contains the supermassive black holes of the early galaxies. The same cosmos that contains all the empirical pressure on the standard model. You are part of it. You always have been. You always will be. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.